For this experiment, Li Hui took the lead. As usual, we started shortly after listening to the briefing from Dr. Nyo. Due to the technical issue, the DSC machine was not operational, so we could only prepare the sample without obtaining results. However, Dr. Nyo mentioned that she would share her result with us. First, we weighed 15 mg of each chocolate sample, white, dark, and milk. Using tweezers, we place each sample into a standard aluminium pan and cover it with a lid. Dr. Nyo mentioned that each box of these pans cost 1,000 ringgit, emphasizing the need to handle them with care. After covering the pans with lids, we used a sample pan crimper to secure them, ensuring the lid and the pan were tightly sealed. We then used a needle to poke a hole to release any internal pressure. With these steps completed, we were ready to load the sample into the DSC machine. However, due to the machine's technical problem, we couldn't proceed. Hence, we then waited for Dr. Nyo to explain how the DSC machine works. She showed us the machine and explained that while operating it is straightforward, interpreting the result is complex. She noted that chocolate is already one of the simplest samples to analyze using the DSC machine. Next, we can discuss the thermal properties of chocolate based on the average peak temperature value shown here. There's an experimental error here, as information from the internet indicates that dark chocolate, which has the highest percentage of cocoa solid, should also have the highest melting point among these three types of chocolate. Cocoa solid are difficult to melt, which suggests that dark chocolate should exhibit the highest melting temperature. Dark chocolate does not have any milk solid added. It generally has a higher percentage of cocoa solid, ranging from 30% to 80%. This higher cocoa content gives dark chocolate a fuller, real chocolate taste and result in a drier, more chalky texture. The high cocoa content also increases the melting point and the energy required for phase transition. Milk chocolate should have an intermediate melting point. Milk chocolate contain at least 25% cocoa solid produced from various proportion of the non-fat part of the cocoa bean. It should also have at least 10% chocolate liqueur and at least 12% milk solid. Additional ingredients often include cocoa butter, vanilla, milk fats, and lecithin. The presence of milk fats and proteins lowers the melting point and reduces the energy needed for melting. While white chocolate, which contains no cocoa solid, should have the lowest melting point. Instead, it is made from cocoa butter, a pale yellow edible vegetable fat with a cocoa aroma and flavor. The absence of cocoa solid affects its thermal properties. It requires less energy to melt due to the lack of complex solid structure. Next, different types of chocolate have different composition and structure. It depends on numerous factors such as the presence and quality of fat, addition of sugar, and particle size distribution of chocolate. Milk fat present in both milk and white chocolate has a lower melting point than cocoa butter, reducing the overall melting point of the chocolate. Hence, the melting point of dark chocolate is higher than that of milk and white chocolate because it does not contain any milk. Additionally, the sugar and milk solid in milk and white chocolate interact with the cocoa butter and milk fat, resulting in a more complex melting process at a lower temperature compared to dark chocolate. Cocoa butter influence. Cocoa butter's proportion and crystalline structure significantly influence the thermal properties of chocolate. Cocoa butter has polymorphisms, meaning it can form 6 different types of crystal with different melting points. The processing conditions, such as tempering and the formulation of the chocolate, determine the crystalline form present in the final product, thus affecting the thermal profile. Different types of chocolate have varying amounts of cocoa butter and different crystalline forms, which melt at different temperature. Next, we move to different application of TGA and DSC. TGA is commonly employed to assess material characteristics such as polymer degradation temperature, absorbed moisture content, levels of inorganic and organic compounds, decomposition, points of explosives, solvent residues, and to estimate corrosion kinetics in high temperature oxidation. Whereas, DSC is primarily used to study phase transition like melting, glass transition, or exothermic decomposition, detecting energy changes or heat capacity changes with high sensitivity. Due to the DSC machine malfunction, we use YouTube to learn its operation, showcasing our initiative. We share knowledge and resources as team members, like we share the YouTube link we found and some information from the internet, which also help improving our understanding and preparation for the experiment. To set the goal, even though this was our last experiment for this module, in the future, if the machine malfunction, we can still use various learning resources such as videos, academic papers, and textbooks to expand our knowledge. Deepening our understanding of DSC analysis and other thermal analysis techniques will better prepare us for the future experiment. Some of the modest points as I conclude from this experiment are: we need to ensuring the accuracy in sample preparation, particularly with the sample pan crimper, handling the expensive standard aluminum pans as emphasized by Dr. Nyo, and realizing the need to place the lid carefully as accidentally pushing the pan and sample out, which will lead to contamination. The most surprising aspect of this experiment included the high cost of the standard aluminum pans, which over 1,000 ringgit per box, emphasizing the need for careful handling, while operating the DSC machine seems straightforward, and the real complexity lay in accurately interpreting the result. Additionally, the necessity of using a needle to poke a hole in the sealed sample pans to release internal pressure was an unexpected detail. Here are my reference link, and thank you for listening.